Hey everyone, and welcome back to the channel. It's fascinating to think that just back in 2005, the global battery industry was already raking in something like $48 billion.
Wow, 48 billion.
Yeah. And of course, that number's just been climbing ever since, which really goes to show you how important electrical energy is becoming.
For sure. I mean, it just underscores that our need for portable power, and electricity in general, it's only going up.
Absolutely. And that actually brings us perfectly to today's topic, which is electric power. We're your AI experts, and we're here to help you guys understand this really foundational concept in electronics engineering technology.
Exactly. You can kind of think of electric power as like the heartbeat of any electrical system. It's basically the rate at which that electrical energy is getting transferred.
I like that, the heartbeat.
Okay.
Okay, so let's try and break this down a little further. If we're trying to explain this to someone who's like totally new to electronics, where do we even begin?
Well, imagine you have like a water pipe, right? So the water pressure, that's like the voltage, it's pushing the water through.
Okay.
And the amount of water flowing through that pipe, that's like the current. So electric power is essentially a measure of like how much water is being pushed through at any given time.
So the higher the pressure and the more water flowing, the more like power we have.
You got it.
Yeah.
Now, in electronics, we actually measure this power in something called watts. You've probably seen this on like light bulbs, appliances, things like that.
Right, like a 50-watt bulb or like my 1,000-watt microwave. Okay, so then how do we actually calculate this wattage? Is there like a formula or something?
Yeah, there totally is. It's really simple. Power in watts is just voltage times the current. We usually use the letter P for power, a V for voltage, and then I for current.
Okay, so P equals V times I. Got it.
Exactly.
So I remember learning about like different types of components and circuits. How does it all play into this?
Right. So we have what are called active components, and then we have passive components. Active components are kind of like the power source. They're like the pushers in our water pipe analogy. They basically convert other forms of energy, like say the chemical energy that's in a battery, into electrical energy.
So they're the ones supplying the pressure in our system.
Yeah, exactly. And then on the other hand, we have our passive components, which are the ones that are actually using the electrical energy. They're kind of like the faucets or the sprinklers in our analogy.
Okay.
They convert that electrical energy into other forms like, light or heat or motion. Think of things like light bulbs, heaters, motors.
Okay, so active components are providing the power.
Yeah.
And then passive components are the ones actually using it. Gotcha.
Exactly. And you know what? It actually gets a little bit interesting here because some components can actually act as both a source and a load, like depending on what's going on. A good example is like a rechargeable battery. When it's powering your device, it's acting as a source, right? But then when you plug it in to charge it up, it actually becomes the load. Then it's drawing power from the outlet.
Wow, so it's not always so black and white. Is that why we have things like the passive sign convention? I kind of remember that term from electronics classes.
Exactly, yeah. It's really just a way for us to keep track of which direction the power is flowing in. So we say that if the power is flowing out of a circuit and into a component, like into a load, that's positive power.
Okay.
But then if it's flowing into a circuit from a component, like say from a source, then that's considered negative power.
So even though a power source is, supplying the power, it technically has like negative power consumption.
Yeah, exactly. It just comes down to perspective and having a standard way to describe it. Now, to simplify things a bit, let's just focus on a specific type of circuit for a second. We call these resistive circuits.
What's special about those?
Well, in resistive circuits, the relationship between the voltage, the current, and the resistance is like very predictable. And because of this, we can actually combine our power formula with something called Ohm's law to get a few more like really handy formulas for figuring out the power.
Wait, so there's more than one way to calculate power in a circuit?
There is. We can also use these formulas. P equals I squared times R, or P equals V squared divided by R, where the R represents the resistance of the circuit.
So if I know any two of those values, like voltage, current, or resistance, then I can just figure out the power, just like that.
You got it. Now keep in mind, this works great for what we call DC circuits, or like direct current circuits. That's where the current's flowing steadily in one direction. But things get a little more complex when we start dealing with AC circuits, which is, alternating current.
Right. AC is what we use in our homes, and the current's constantly switching direction. How does that change things?
Well, that back and forth flow, it adds a whole new layer of complexity, especially when we start throwing in components that store energy like capacitors and inductors.
Okay.
These guys can actually cause the energy flow to like periodically reverse.
Okay, this is definitely getting a little bit more complicated.
It is. It's not as simple as just multiplying voltage and current anymore. With AC circuits, we have to start thinking about real power, reactive power, and apparent power.
Whoa, hold on. 3 types of power now. I'm starting to feel a little overwhelmed.
No, don't worry. We'll break it down. Think of it this way. Real power is like the portion of the energy that is actually getting used to, do work.
Right.
Like lighting a bulb, running a motor, that kind of stuff. It's like the useful power,
So it's what we're actually paying for on our electric bill.
Exactly. And then we have reactive power. This is the portion that's kind of bouncing back and forth between the source and the load.
Okay.
And this is because of those energy storing components we talked about. So it's not actually doing any useful work, but it still takes up space in the wires and things.
So it's kind of like wasted power.
Kind of, yeah. And then lastly, we have what's called apparent power, which is basically the total power that the circuit needs to be able to handle. It includes both the real and the reactive power.
So it's like the total capacity of the circuit, while real power is the actual usage.
Exactly. Perfect analogy.
Yeah.
Now, the ratio between those two, it gives us something called the power factor. And that tells us how effectively the circuit's actually using the power it's given. But let's zoom out for a sec. Did you know that electrical energy isn't just limited to wires and circuits?
Oh.
Yeah, it's actually flowing wherever electric and magnetic fields coexist, and they're fluctuating.
Wait, seriously? So there's electricity happening all around us right now?
Yeah.
Not just in our devices?
That's right. Now, calculating the power in those situations, it involves some more advanced math, but that same basic concept of energy transfer, it still applies.
Okay, you've officially blown my mind. So we've talked a lot about consuming power, but where does all this electrical energy actually come from in the first place?
That's a great question. That leads us into the world of power generation. And there are basically 2 main ways that we produce electrical power. We have what's called centralized generation, and then we have distributed generation.
Centralized versus distributed, what's the difference?
Well, so centralized generation, think of those massive power plants you see. The ones that often rely on things like fossil fuels or nuclear reactions or hydropower.
Okay.
They generate electricity in the central location, and then they distribute it out to all the consumers over long distances.
So those are like the powerhouses of our electrical grid. What about distributed generation?
Distributed generation is more about producing power closer to where it's actually being used. Think things like solar panels that are up on rooftops or wind turbines or even small-scale generators.
So it's about bringing power generation closer to home. Literally.
Exactly. And you know what? This whole trend toward distributed generation, it's really rapidly changing how the energy landscape looks, especially with the rise of renewable energy sources. It's a big part of why understanding electric power is becoming more and more important these days.
This has been really insightful. We've covered so much already, from like the basics of electric power to how it's produced and how the energy industry is changing. We could probably talk about this for hours.
We could, and we really are only scratching the surface here, but I think it's a good point to pause for a sec and let everybody process everything we've talked about.
I agree. But before we move on, I want to remind everybody that we're just AI experts here, and this is all for informational purposes only.
Absolutely. Welcome back, everybody. Before we took a moment to hear your thoughts, we were talking about the 2 main methods of generating electric power, centralized and distributed.
I'm actually really curious to dig a little bit deeper into how these methods actually work. Let's start with those big centralized power plants. What kind of technologies are they using to make all that electricity?
Well, the main workhorses are the ones that have been around for a while. Fossil fuels, nuclear power, and hydropower.
Okay, yeah, those are the ones that I've heard of. Can we break those down one by one? Let's start with fossil fuels. So how do we actually get electricity from burning stuff like coal and oil?
It really all boils down to heat. When you burn fossil fuels, you're creating a ton of heat energy. And then we use that heat to boil water, which produces steam, high-pressure steam. And then that steam spins these things called turbines, which are connected to generators. And the generators, those are what convert that spinning motion into electrical energy.
So it's like a giant industrial-scale tea kettle, and it's using the steam to power a generator. That's pretty cool. What about nuclear power? How's that different?
Well, the basic principle is the same. You're still using heat to create steam to spin the turbines. But instead of burning fossil fuels, nuclear plants use nuclear fission.
Okay.
And that's basically where you split atoms, and that releases a huge amount of energy, which is in the form of heat.
So same end result, but different heat source. Are there any pros and cons to each method?
Oh yeah, definitely. I mean, fossil fuels, they're still relatively abundant. They're pretty cheap. But the problem is they release greenhouse gases and other pollutants. That's a major contributor to climate change and air pollution.
Yeah.
Nuclear power, on the other hand, it doesn't release any greenhouse gases when it's operating. But you do have to deal with radioactive waste, which needs to be very carefully managed and stored.
Okay, so each has its own set of challenges. What about hydropower? So how do we actually make electricity from water?
Well, with hydropower, what you're doing is harnessing the energy of moving water. So think of like a dam, right? You have this huge reservoir of water held back by the dam.
Right.
And then when you release that water, it flows downhill with a ton of force, and that spins turbines, which, like before, power the generators.
So you're using gravity and the natural flow of water to generate electricity. Pretty clever.
Yeah, it is. And it's generally considered a renewable source of energy because the water cycle naturally replenishes those reservoirs.
Okay.
But there can be some environmental impacts, especially with, the construction of dams. It can disrupt river ecosystems.
Interesting. So each of these centralized methods, they've got their own pluses and minuses, but it sounds like they all require this massive infrastructure to work.
Mm-hmm.
What about distributed generation? So those smaller scale methods you mentioned, like solar and wind power, how do those work?
Okay, so solar panels, those use things called photovoltaic cells. Basically, these cells absorb photons that are coming from the sunlight, and these energize electrons, creating an electrical current.
Wow, so it's like the sunlight is literally transformed into electricity. That's amazing. What about wind turbines?
So wind turbines, they use those big giant blades that you see to capture the kinetic energy of the wind.
Okay.
And then when the wind spins those blades, it also spins a shaft, which is connected to a generator, just like we saw with those other methods.
So it's kind of like hydropower, but you're using the wind instead of the water to spin the turbines.
Yeah.
These distributed methods, they sound a lot cleaner than burning fossil fuels.
They are. Solar and wind power, they're both renewable. They don't produce greenhouse gases while they're operating.
Right.
But, the one downside is that they're intermittent.
What does that
mean? Meaning they're dependent on the weather. So the sun's not always shining and the wind's not always blowing.
Right. You can't control Mother Nature. Are there any other ways to generate electricity on that smaller scale?
Yeah, there are a few others. Fuel cells are a really interesting technology. They convert chemical energy from fuels, things like hydrogen, into electricity. And then there's also geothermal power, which is tapping into the heat energy from within the Earth itself.
Wow, it seems like there's a whole world of options out there when it comes to this distributed generation. It sounds like the energy industry is becoming a lot more diverse.
Oh, it absolutely is. There are so many factors that are driving this change. We have advancements in renewable energy technologies, growing concerns about climate change, and even just the desire for energy independence. It's a really exciting time to be following this field.
Absolutely. So what are some of the other, big trends that are shaping the future of electric power?
One of the biggest is definitely the rise of these things called smart grids.
Smart grids.
Yeah, these are basically power grids with a brain. They use digital technology to monitor and manage the flow of electricity.
Okay.
So they can make the grid more efficient, more reliable, and more resilient.
So it's like giving the power grid the ability to think and react in real time.
Exactly.
That's incredible. What else is changing?
Another huge trend is the growing importance of energy storage.
Okay.
So as we keep adding more and more of those intermittent renewable sources to the grid, solar, wind, things like that, we need ways to store the energy that we produce when the sun is shining or the wind is blowing so that we can use it later when those sources aren't available.
Right. That makes sense. That's where those massive battery systems that we're seeing more and more of come in, right?
Exactly. Batteries, they're becoming absolutely crucial for grid-scale energy storage. They can take that excess solar or wind power and hold on to it and then release it back into the grid when it's needed.
So it's almost like the batteries are acting as these giant energy banks to help balance out the fluctuations from the renewables. This is all so fascinating. It feels like the electric power industry is like right on the edge of a major transformation.
It is, and these changes are paving the way for a more sustainable, more resilient, more decentralized energy future. It's been quite a journey today, hasn't it?
It really has.
We began with this very basic idea of electric power, and now here we are talking about giant power grids and renewable energy sources and like the future of energy storage.
Yeah.
And as we move toward a more, sustainable and decentralized energy future, understanding these concepts is just becoming more and more crucial.
So true. So we'll be back with more deep dives into this awesome world of electronics engineering technology very soon.
Very soon. And don't forget to subscribe to our channel for more fascinating deep dives into the world of science and technology.
Thanks for joining us. See you next time.